Okay, so we've just finished talking about, there we go. We just finished talking about, the second derivative test, max and min, all of that. So today we're going to talk about the first derivative test and concavity. So the first derivative test. So this is used to find what your relative extrema are. So we found relative extrema before. This is just building off of if you're asked to find increasing and decreasing, then you can use this to find it. So let C be a critical number of a function f that is continuous on the open interval containing C. If f is differentiable on the interval except possibly SC, then f of c can be classified as follows. So if the first derivative changes from negative to positive, then f has a relative minimum at cf of c. If it changes from positive to negative, then it has a maximum. So negative to positive, so decreasing to increasing or increasing to decreasing. And if it doesn't do either of those, then it is neither a max or a min. So decreases right here at this point is where it changes. Oh, sorry. And then it increases. So decreasing to increasing gives you a min. Increasing to decreasing gives you a max. So at that point is where you have a relative max and a relative min. So an example, find the relative extrema of a function, f of x equals 0.5x minus sine x, and determine where the function is increasing and decreasing. So like everything else, we are going to start by taking the first derivative. So go ahead and do that. If you need to pause it, then please do. Remember, this will move quickly, but you're welcome to pause anytime. Okay, first derivative, 1/2 minus cosine x. To find our critical values, we have to set that equal to 0 and solve for x. So remember, when we're solving for x, we're trying to see where does cosine equal 1/2. Okay, what makes cosine equal to 1/2? Well, if you put pi over 3 or 5 pi over 3 in, you get 1/2 out. So we were given an interval here, so remember you put them in order. So our first one is going to be 0 to pi over 3, pi over 3 to 5 pi over 3, and then 5 pi over 3 to 2 pi. Our test value, you were just choosing a number between these two numbers. So a number between 0 and pi over 3, I chose pi over 4. When I plug pi over 4 in, what do I get? Negative or positive? In this case, I get the derivative to be negative, meaning it is decreasing. Sorry about that. Meaning it is decreasing. Okay, and so next one, a number between pi over 3 and 5 pi over 3 is pi. I plug pi into my first derivative, which gives me 1/2 minus -1. So minus and negative is positive, meaning that derivative of f at pi is greater than 0, meaning it's increasing. And then my last one, I chose 7 pi over 4. Remember, you could choose anything, any number that's between these two numbers. This is just what I chose. You do want to, it would make sense to choose easier numbers to work with, things that you know, but it doesn't mean you have to. And this is less than 0, so again it's decreasing, but that's not what we were asked to find. If you recall, we have to also find the extrema. So what is the maximum and what is the minimum of the function? Remember that max and min happens whenever your function changes directions, essentially. So it changes from negative to positive or positive to negative, meaning at pi over 3 and 5 pi over 3, we change. One we go decrease to increase, the next we go increase to decrease, meaning we have a relative minimum at pi over 3 and a relative maximum at 5 pi over 3, because it goes decreasing, hits pi over 3, and then it starts to increase. And then up here it goes increasing, hits 5 pi over 3, and it starts to go back down. So that's where your minimums and maximums are. Okay. So again, find the following function, increasing, decreasing, use the first derivative test to find the relative extrema. So you're going to do the same thing that you just did. If you want to pause it here so you can try and work through it and then check your work, would be great. You're going to start by taking the first derivative, set that, or I rewrote it to make it look nicer. Then set it equal to 0. When this is 0, that's when your function is 0, so, or undefined as well. So in this case, we get 0, -2, or 2. 0 in the top, and then -2 and 2, plugging in the bottom. Because they didn't give us any overlying intervals, we're using -infinity, infinity. So again, we go in order. So -infinity to -2, -2 to 0, 0 to 2, and 2 to infinity. You want to pick a number, so I'm going to do them by column, the green, blue, yellow, then gray. So -3 is between -2 and -infinity. If I put -3 into the first derivative, I get my function to be less than 0. If it's negative, that means it is decreasing. Between -2 and 0, I chose -1. When I plug -1 in, I get my function to be, greater than 0, which means it's increasing. Between 0 and 2, I put 1. When I plug 1 in, I get my function to be less than 0, my derivative, and then decreasing. And 2 and infinity, I chose 3. When I plug 3 in, you get greater than 0, and if it's greater than 0, that means it's increasing. Remember, again, you have to find the extrema. So you want to look at what's happening at these points, and because it's going from smaller, 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 it eventually plateaus and then starts to increase, meaning at -2 is where that happens. Okay? So -2, 0. If I plug -2 into my equation, I get 0 out. The next spot at 0, and remember, sorry, this is back into your original if I plug -2 in. At 0, it's increasing and then it changes to decreasing. So 0 has a maximum. If I plug 0 in, I get 0, about 2.52, and then at 2 it's another minimum, and that is 0. So, okay, concavity. The definition of concavity: let f be differentiable on an open interval, then the graph is concave up if the first derivative is increasing on the interval, and concave down if it's decreasing. If it's concave up, then the graph lies above all of its tangent lines. So remember, tangent line touches the graph exactly one time in those spots. So that's what that means. And if it's concave down, if the graph lies between all of the tangent lines, or I'm sorry, below all of the tangent lines. So test for concavity. So the test for concavity, you're going to use second derivative. And if the second derivative is greater than 0, then it's concave up. So if it's bigger, then it's up. If it's less than 0, then it's concave down. So we're using second derivative now rather than the first. So just keep that in mind when we do our example problems. So determine this. So like I just said, we are using second derivative. I'm going to rewrite this so it looks nicer and it's easier to work with. Okay, so to get the second derivative, you have to take the first derivative. First derivative gives me this, and again I'm going to rewrite it again to make it easier to find the second derivative. If you didn't choose to rewrite it, if you left it like this, you would be doing product rule, chain rule, lots of things going on. So I rewrote it, and I'm just going to use quotient rule, which is low d high, high d low, all over low squared. So when I do that, you're going to get a long, messy thing, something like this. And I'm going to show you the simplified answer. Again, you should make sure you can simplify it on your own. So if you want to pause it and do that and see what you get, that would be great. So when I simplify it, I get 36 times the quantity x squared minus 1 over x squared plus 3 quantity cubed. And okay, so before we were setting the first derivative equal to 0, but when you test concavity, you're going to set the second derivative equal to 0. So this is going to set equal to 0, and that's going to give us our test intervals. So when does this equal 0? Well, the bottom never goes to 0 because you're adding and squaring, meaning no matter what you put in, you're going to get a positive number. So we just have to worry about the top. And what makes this go to 0? Well, it goes to 0 when x squared minus 1 is 0, which is when x equals negative or positive 1. Again, we weren't given an overbearing interval, and so we're going to use negative infinity to infinity. So we have negative infinity to negative 1, negative 1 to 1, and 1 to infinity. A value in between here, I chose negative 2. So when I plug negative 2 into the second derivative, so into this, I get that to be bigger than 0. Remember, if it's bigger, that means it's concave up. Negative 1 to 1, I chose 0. If I plug 0 in, then that means it is less than 0, making it concave down. Okay, sorry about that. And then if I chose, and here I chose 2, and if I put 2 in, it is bigger than 0, meaning it's concave up again. So you're just using the second derivative now to find concavity. This part is not on your homework, but I do give you classwork problems at the end. So the part for your homework was just the first derivative test. Okay, last thing, point of inflection. Let f be a function that is continuous on an open interval, and let c be a point on the interval. So remember, c is just a number. So if the graph of f has a tangent line at this point, cf of c, then this is a point of inflection of the graph of f. If the concavity changes of f from upward to downward, downward to upward at that point. Really what it's saying is if cf of c, so a point on the graph, it's a point of inflection if the second derivative equals 0 or does not exist. So back here, this would be at negative 1 and 1, because at negative 1 and 1, my derivative is 0. If I put negative 1 into this, I get 0, which this says right here, the second derivative has to be 0. So negative 1, and then whatever I got when I put negative 1 into the original. So let's see, negative 1 squared is 1, plus 3 is 4, so 6 over 4. So my point of inflection would be negative 1, 6 over 4, which is 3 over 2. And the other point of inflection would be 1, because both of those make my second derivative go to 0. Okay, so that's all that means. Okay, so here are some try problems. You can complete them as classwork. Make sure you do them though. I will be checking them. If you have questions, again, feel free to email me anytime. I will try and check my email as much as possible. And I hope you are all having a wonderful break and a happy 2 days off. Enjoy your time with your family and friends. Bye.